Okay, we're looking at section 7.2, finding complex solutions of polynomial equations. So to start off with, we're going to look at the number of solutions, or just number of zeros for a polynomial function. So we've used different methods to find the roots. So because a polynomial can have a factor that repeats, a zero or a root can occur multiple times. So if a root occurs multiple times, it says it has a multiplicity. So the multiplicity of a zero is the number of times the factor occurs in the factorization. So here we have x plus 3 squared, so that means it has a multiplicity of 2. So if we want to find all of the zeros in this function, x cubed plus 7x squared, include any multiplicities that are greater than 1. So first thing we do is factor out the greatest common factor, which is an x squared. So if we think about what are the zeros, we set each of our factors equal to 0 to find out what those zeros are. So our zeros will be at -7 and 0, which has a multiplicity of 2 because it's coming from the x squared. Similarly, here we want to find all of the zeros. So this is a difference of 2 cubes. So it will factor to become x minus 4, x squared plus 4x, plus 16 from the difference of cubes rule. So we want to find the real zeros. That's coming from the x minus 4 part. If we set the x minus 4 equal to 0, we've got a real solution at x is 4. The x squared plus 4x plus 16 we know is irreducible. So that means we're going to have to use the quadratic formula. So plugging in the pieces here, we've got negative b plus or minus b squared minus 4ac all over 2a. Under our square root, we're going to have a negative 48. That tells us we're going to have imaginary solutions, which means we're going to have an I. 48 breaks down into 16 and 3. 16 is a perfect square, so we take the square root of that, which is 4, pull it outside along with our I, and then that 3 is going to stay inside. So we can simplify from there to get the negative 2 plus or minus 2i root 3. So the non-real zeros would be negative 2 plus 2i root 3 and negative 2 minus 2i root 3. We want to find all of the zeros of this function. We can factor out the greatest common factor of x, leaves us with x cubed plus 3x squared minus 4x minus 12. We want to do factor by grouping. We can set that up here. Pull out our terms. We'll have an x squared here and then a 4 here. Regroup. So we'll get the x squared minus 4 and the x plus 3. X squared minus 4 is a difference of squares, so it factors to become x plus 2, x minus 2. So in this case, if we're looking at the zeros, again, we set each of those factors equal to 0. And then our zeros are at 0, negative 3, negative 2, and positive 2. We want to find all of the zeros of this function. So this is a difference of squares. Actually, the fourth is a perfect square. 16 is a perfect square. So it factors to become x squared minus 4, x squared plus 4. Now x squared minus 4 is another difference of squares. So it factors to become x plus 2, x minus 2. That's going to get us our real zeros of negative 2 and positive 2. Now we can solve x squared plus 4 equal to 0 by taking square roots. So we subtract the 4, take the square root, plus or minus the square root of negative 4. Negative under the square root means we'll pull out an I. 4 into the square root of 4 is 2. So x plus or minus 2i, so that means our non-real roots would be 2i and negative 2i. And working through one more of these, we can factor this. We'll get x minus 1, x plus 1 to factor out. We're left with x squared plus 4x plus 4. And this quadratic is a perfect square trinomial. It's actually going to factor to become x plus 2 squared. Now, since we already had that x plus 2 up here, it factors completely to x minus 1 times x plus 2 cubed. So what are the zeros? We set each term equal to 0. Our zeros are at 1 and -2. That -2 has a multiplicity of 3 since it's to the third power. Well, what does this tell us? So we can factor these over the integers. We showed that already. If we find the zeros and their multiplicities, we did those already. The key thing here is that the power of the highest power of your function is going to be the same as the number of zeros you have in total. So both the real and the non-real, your total number of zeros is the same as the power of your function, including the multiplicities. So like the first one here, we only have 2 zeros, but because 0 is a multiplicity of 2, that counts as 3 total zeros. Same thing down here at the bottom. X to the 4th is our highest power over here. We've only got 2 zeros, but -2 has a multiplicity of 3, so that works out. So that's essentially what the corollary here is telling us. For every polynomial function of degree n greater than 1 has exactly n zeros, including multiplicities. So whatever the highest power is, that's the number of zeros that your function is going to have. So how do we use this? First thing we do is determine the number of possible zeros. So that's the biggest exponent. So in this case, our function is going to have 3 zeros. Next, we use a graphing calculator to find as many zeros as we possibly can. So I'm going to pull this up here on my graphing calculator. We're going to see how many zeros we can get. So we've got what? 2x cubed minus 12x squared minus 34x plus, there we go, 204. So what we're doing here is we're going to graph this. We're going to look and see where it crosses the x-axis. That's where our zeros happen. Oh, what's my window at? Sorry, my window is not in standard form. Oh, I guess it is. Well, I think I inputted something wrong then because it's not matching up to my answer. So let's double check our function here. 2x cubed minus 12x squared minus 34x plus 204. I'm having an issue. Well, let's check our table here. Must have messed up somewhere. So come back here on the next video. I'll figure out where I went wrong, and hopefully we can fix whatever my mistake is here.